Right, well, welcome Adam, welcome everybody to the second session. My name's Jeremy Tavery, I'm the Dean of Faculty of Life Sciences. I've known this guy for a while, love him to bits. Valeska, this is a great night for you guys. It's a very important night for both of you. This is a unique event to have both of you doing this. I'm really proud of both of you, thank you. Great talk, Valeska, I just hope this guy is up to the standard. In fact, we shared this is a great moment for you. We shared a great moment many years ago, 2014. He drank my credit card. Valeska was there, but we couldn't control him. My son got 100 on debut for Gloucestershire, opening the batting. These guys were both there with me. It was an incredible day for me. I left my bank card behind the bar. I was quite surprised by the cost when I got home. But anyway, there are lots of others drinking it as well. But that was a great moment for me, and I'm just really pleased to share this really unique and great moment with you guys. Love you to bits, both of you. Thank you. So. Well, we've already heard Adam was promoted to professor in 2019, and it is right that we do these inaugurals in person. It's so much better that we can all celebrate together. So it's definitely been worth the wait. Adam is the Professor of Bioengineering in the School of Cell and Molecular Medicine. And again, when you hear him, you'll realise he's Antipodean if you don't know already. And he started his academic training at James Cook University. I'm sure we're going to hear a little bit about this, and then moved on to ANU, which we've already heard about. And you worked with John White, FRS, at the ANU, where you did your PhD. And then he decided to come all the way around the world in 2007 to Bristol, to the School of Chemistry, and then I think you got an EPSRC fellowship in 2010, then you transferred onto a We didn't transfer onto it. You won a lectureship in the School of Cell and Molecular Medicine in 2013, and then you became professor in 2019. Many accolades in your career so far, and I'm sure there'll be many, many more. We're going to hear about your research, which again is very kind of materials-based in biological systems, hybrid biomolecular systems, mixing physical science with chemistry. I guess you do a bit of mathematics as well, maybe a bit of modelling. Maybe Valeska does that for you, actually. So what do you talk about at breakfast and dinner and, you know? Yeah, it's all parked, isn't it? You were recognised with a Wellcome Trust Frontiers Innovator Award in 2015. I know you're very proud of that. And 2016, you were awarded the Biophysical Society's Young Investigator Award and Medal, the British Biophysical Society. You know, really prestigious awards. So well done, Adam. And then, even more prestigious, he was awarded one of the very first UKRI Future Leaders Fellowships, which, when you're going into a competition like that and you don't know what the rules are, to get one of the first in the first round is really staggering. And I'm really proud of you for that. Loads of media coverage. TV, BBC4, in all sorts of places, New Scientist, Nature, The Chemical Engineer, I could go on, Chemistry World. And then in 2017 you founded the cell therapy technology company Cytoseq. You've just raised a really important round of funding. Is it 4 million?
3.6.
Oh,
yeah,
I exaggerated.
yeah.
3.6 million. You know, to take your technology into a practical application, I think that's absolutely fantastic. That mix of private enterprise, innovation, entrepreneurship, together with really fantastic fundamental science. It's really unique. So, congratulations, Adam. You hugely deserve this, and I'm really looking forward to your lecture And maybe we can just swap seats.
Yeah, sounds
Over
good.
to you.
Thanks, mate. Tav's been my mentor for many years. And it is obviously really a tough act to follow. I did promise that I would just take it down a notch to not make Valeska look bad. And really, what's important is I'm pretty sure Rutherford was born in Australia. I think I'm not quite sure about that. So I'll kick off a little bit with switching this on. And, talk about myself, which I guess most of you know, it's one of my favorite topics. So, this is the easy part of the lecture, really. And so my interests, obviously, in chemistry, which we did quite a lot of, at ANU and across my life. Marine biology, I'm a big fan of. And of course, I like technology. And Tav sort of covered this already. I started off at James Cook. And I'll step you through a little bit the journey, and then to ANU for my masters or honours, as we call it in Australia, and then over here to chemistry and the various fellowships between chemistry and CMM. And really, what I'm all about is interdisciplinary science. It keeps it interesting. I guess the core training for me was in biophysics and physical chemistry and colloid chemistry, and just trying to think about how matter fits together, and then. I went from, a person was interested in understanding complex processes to wanting to make things. And during that career, I sort of jumped between sort of biophysics and bio-nanotech, tissue engineering, 3D bioprinting, and more recently, really, cell therapies. So how did I end up here? I guess, well, first of all, I started off at James Cook University, and that's the old library there, which looks a little bit like a boat, which is probably handy in the tropics because they get flooded out all the time. And then it was a Thursday afternoon. You have all these things in life where a random conversation turns into a complete life-changing situation. And it was a Thursday afternoon. I was chatting to a lecturer. I was in third year, and I was like, "What am I going to do?" And up in North Queensland, if you're a bright chemist or something, you might go and work at a power station or a refinery or a mine site, earn some money over the Christmas break, and then you'd go back to uni. And I was like, I don't want to do this. I was starting to get really interested in chemistry. And he said, oh, ANU have these scholarships that you can apply for. And I went, oh, okay, yeah, cool. So, I think I physically wrote a letter, and that's how old I am now. And I wrote this letter. I had a look at this yearbook, I had from, the Research School of Chemistry at ANU, and looked through the people. And I couldn't decide, do I become an organic chemist? I was really close. I topped organic chemistry, and I was like, yeah, maybe I'll be an organic chemist. But I really like physical chemistry. And I went, I'll take physical chemistry, and if I don't like it, I can always change later. So I looked through the people that work there, and there's this guy, Rick Pashley, and I was like looking at stuff, colloid surfaces. Oh, that sounds pretty cool. Dear Rick, dear Professor Pashley, send this letter off, and then about, a few weeks later, I got this letter back. Congratulations, you've got a scholarship to come and study here, Professor John White. And I was like, who's John White? So I go back, this guy. It turns out the yearbook was about 3 years out of date, and this guy, Rick Pashley, had moved to another university. So luckily it got picked up by John. Anyway, so I moved, sort of from where I'm from, the reefs here, all the way down here. Like I said, it's about a 53-day walk, or as we travel in Australia, if you take a big red kangaroo, it's about 30 hours. And that's what it would probably look like if it had to drag my ass all the way down to, to Canberra. Anyway, so here we are. So this is the Research School of Chemistry as it was. After the organic chemists got to it, it looked like this when it was on fire. They're actually not clouds. That was smoke. And that was the end of the PhD. It was sort of terrifying. It sort of blew up a little bit. It wasn't me. I was down here. This is where you always put the chemists, organic chemists, because they're most likely to blow stuff up. And then they basically, a couple of coats of paint, a bit of a tweak, and it looks like this now. So they've done a really amazing job. But the thing was, what drew me to that work was really, again, it was sort of all about proteins, and it was all about proteins and interfaces. And for the non-biologists here, proteins are really big biomolecules. So if you think about water, has a molecular weight of 18. A protein could be between 10,000 and 1 million Daltons, let's say. And what's really intriguing is that they're one chain of spaghetti, and they fold into this very, very well-defined conformation. Every time. And so when I went to ANU, the sort of question was, well, if you take this sort of structure, that's fine when it's floating around in water or in plasma or in buffer. But what happens to it when it starts to stick to interfaces? So the air-water interface. So if you have, if you look at a glass of water and you had protein in it, actually you have a very high concentration of protein at the surface because they're a little bit like detergent molecules. And this sort of drives how they fold. It's one of the reasons that those proteins coil up like that. Because on the inside of it, you have this sort of red here. This is actually I managed to get a copy of my thesis online, and actually this is from my thesis, which is why it looks pretty grainy. But the red's the hydrophobic bits. But if you take something that goes from in solution where it's sort of designed to be there, but if it's up this interface, then all the red bits now all of a sudden they're hydrophobic. They want to be in the air. And so the whole PhD was going, what is the effects of the air-water interface on protein structure? Does it destabilize the protein structure? How do they orientate? And so to do this, again, Valeska and I had an ongoing competition in our PhDs to see how many, it's pretty bad now we think about carbon, how many international flights could we be doing? And to do neutron experiments back then, you had to, Australia, the reactor was pretty average. They've got a good reactor now. You had to fly all the way over here. And I think it's where I really fell in love with the UK. I mean, we'd come over a couple of times a year. And we would do experiments. Here's another image. This is modern. When I went over there, this was the building. And it's actually a World War II aircraft hangar where all the instruments were built. And, my thin blood from 40 degrees summer, of course, because this is me in the control room in 2001, like freezing my ass off with a beanie on, just trying to do neutron experiments. And so we use sort of neutrons and X-rays. I should also point out that diffraction is just a subset of scattering, which is what we do. So they only look at one part of it. So we would come over and do this, and what did we learn? So I'm summing my entire PhD up in one very quick slide, that we could work out that how a protein would orientate at the air-water interface, how they would stack, which is really important for not just industrial processes, but just general protein folding, how to interfaces, it might not just be air water, affect a protein, how it stick together, and aggregation, and things like prion diseases or Alzheimer's, Parkinson's. It's all a big part of it. But we were able to also show that this free energy of unfolding, which I'm not going to go into here, but the fact that a bigger number means it's more stable, that the interface actually destabilized the proteins considerably. And so this was really that training. What else happened? We obviously graduated, and then we had a small wedding in Canberra in the Botanical Gardens. And as you do in Australia, we just packed a very small wedding party into a Toyota troop carrier. Honestly, we got the entire wedding party into one giant four-wheel drive. Went down, we got married, and then our parents found out. And so like a year later, we had to come back and do it properly. But that was the ANU days, right? So then I guess I was at this point where I loved understanding things, but I actually wanted to make things. I'm really into making things. I like working on motorbikes. I like building things. And so I was inspired by this idea of biomineralization. It was something I was reading about at the end of my PhD. And basically, I internet stalked or email stalked Steve Mann until eventually he folded and offered me a postdoc. It's sort of how it unfolded. Because I was really interested in what he was doing, and he was one of the kings of like biomineralization. So I was like, okay, this is where I need to be. And I got over here, and I never did anything on biomineralization. Maybe one little piece of work. I moved into this really weird phenomenon of liquid proteins. We made the world's first ever liquid protein, and I'll explain what that is in a second. So it's this idea that, and it was good, Valeska's talk really helped out with this, because she was talking about these interaction potentials between molecules, right? And that hydrogen has a solid, gas, liquid phase diagram, which is really defined quite well by this very basic potential energy diagram, that when atoms are really close to each other, there's obviously repulsive, because at some point they're going to start interacting. Van Waals interactions go off in infinite, into infinity in terms of distance. But at some point here, you have this energy well where the molecules will sit next to each other at a certain distance. When you moved into the nanoscale, this diagram changes, and you end up have this massive energy well here, very sharp. And actually, it was really looking at C60 fullerenes, and they discovered that if you take C60, like a powder of fullerenes, and you heat it up, it'll turn into a gas, you cool it down and turn it into a liquid, but it'll turn into a solid, but it will never ever turn into a liquid. So there was no liquid phase because of how big they were and how sort of sticky they are. They're still at the same distance from each other. And so there was no liquid phase for fullerenes. And of course, proteins are nanoscale objects, they're similar size. And so it was this question of, well, do proteins have a liquid phase? This is dry, right? So if you dry a protein out, can you melt it? If you heat up this dry protein, will it ever go bloop? But it doesn't. So it's the same problem. So the question was, if we put on this repulsive layer on the outside of these, this, sort of, I should probably start the timer, we're going to be here all night. We're like a minute in, right? Then can we achieve this and get these things to melt? And so that sort of, and again, this is building something which had absolutely no function. There was never any intention of making anything useful at this point in my career. And so we worked out a way to do it, and so there's a structure of myoglobin, we did it chemically, we made these chemically supercharged proteins, we would put on these specialized sort of detergent molecules on the outside that would create that layer on the outside of that, and then we showed that with myoglobin, in fact, we could take this freeze-dried, very, very dry protein, and when you heat it up, it would actually melt and form a liquid, and that was the world's first sort of liquid protein. And it was great for publications and that sort of thing. And we did all this other work. We showed that they were folded. And it was really pissing off a lot of biochemistry friends of mine at the time because it seemed like all this work that was written about water's essential and all this, it just didn't seem to be the case. There was definitely a lot of redundancy within the structures of proteins. And we showed they were folded and functional. And we showed all this other crazy stuff. Like they wouldn't unfold until you hit 200 degrees, right? And proteins normally unfold at 70 or 80 degrees. And in fact, we could even make like enzyme versions of these where you just have a blob of enzyme. There'd be no water, no liquid. It would be its own liquid, and you could put a drop of, say, substrate, and it would work. And so, we had an enzyme working at 150 degrees, which had never been done. So, it was really good for big papers, and and really, I guess, fundamental. But at that point, I guess I was probably going through that, sort of classic, existential crisis of why am I doing all this, and what's it really going to mean? And so we sort of started pushing out into other phases. The nice thing about having this corona on the outside was really it was about manipulating protein X interactions. I could control how a protein would interact with solvent molecules to create aerosols, or how they interact with themselves to self-assemble to make materials, or indeed cell membranes. And this has become a very, very big part of what we do in my lab, and also, of course, with Cytoseq. And I'll have a couple of slides at the end about that. So this is some of the examples of what we were able to do with this sort of technology within the materials field. This is fabric here, for example, is a 3D printed protein plastic, enzyme plastic, that you can print at very high resolution. This is it actually breaking down a nerve agent simulant, which is sort of defense-based. This is a plastic which is partly GFP, so green fluorescent protein, and you can print with that, and we could infiltrate. There's a lot of guys who have done this work, so straight out. There's too many people to acknowledge tonight. I'll do a little bit at the end. But you could make a raft of materials and really access things that just weren't possible really in biotech for a long, long time. So then, it was again one of those days where something happened, and I was, I think I was towards the end of my first fellowship, and I was going, well, what am I going to do next? I need to get a job, as we all feel like, I need to get a job. I need something a bit more permanent. And I've been collaborating with this guy in CMM, Anthony Hollander, on sort of this work. And it was probably, I think it was a Thursday as well. And I caught up with him, and I said, yeah, I'm going to start looking at jobs. I'm not quite sure. Maybe I'll stay in the UK. Maybe I'll go somewhere else. And he said, oh, look, we've got positions going in CMM. You should apply. And I went, okay. So he gave me the sort of job advert. And I said, oh, okay, when do these need to be done? And he went, oh, yeah, tomorrow, 9 o'clock. So, and this is like, you had to have a 6-page research vision. And so I went home, and I was chatting to Valeska, and I was like, yeah, well, I don't know, maybe I should. So I read it, and then it said, must have a PhD in biological sciences. And I went, I'm a chemist. So I gave him a call and said, look, and he goes, just apply. So I spoke to Valeska and went, all right, I'm going to stay up all night. I'm going to finish this about 6 a.m. And it's going to make no sense by the end of it because I'll just be speaking smack because I'll be so tired. Can you translate that back into English for me? So I went to bed. She got up. She tidied up at the end of it, submitted, and went get on with my life. And then, of course, as things as things do, they changed. And a lot of the work in CMM has been about this idea of taking again these sort of structures where they have this is the protein and this is the polymer surfactant on the outside of them, And when they come up to an interface, so again, it's all interfacial relationships, that because this is hydrophobic, so this is the membrane of a cell, for example, that this reconfigures, it changes, because again, these hydrophobic bits all of a sudden go, oh, there's somewhere else to be. And what this means is they can then insert into the membrane of a protein. In fact, they even self-assemble, but we're not going to go into that. So another story, and I'm glad Warwick's here, he can validate this, but when we first spoke to Anthony, he said, yeah, with these systems where it's in the liquid protein paper, which had, again, wouldn't be able to use on cells. And I said, we might be able to modify this and make this work to paint cells. So I'd never seen a cell in my life. And so Alice, Warwick's wife now, was working for Dan Davies at Imperial on super resolution microscopy from immune cells. So I just went, okay, I gave her a call and said, look, can I bring my stuff down and can you put it on some cells and image it for me? So I genuinely snuck into his lab. To this day, he doesn't even know I was in his lab. And we imaged these things and it worked really well. So we came back and went, right, this is on. This is how it all started. So again, don't be afraid. Probably notify the supervisors that you're coming, but it wasn't really my style. So it worked, it went on the cells. And then the question was, can we do something useful? So it's maybe one of the first useful things I was doing. That I got into tissue engineering, and for those who don't know, basically multiple ways of doing it. Typically, you would have what's called a scaffold, which would be probably a porous material. You would put your stem cells on there, you throw a cocktail of growth factors on there, and you can get the stem cells to differentiate into different types of tissue. And there's a big problem with this is, in tissue engineering, is that the cells run out of oxygen. They gobble it all up. And if you try to engineer a big chunk of tissue, they all die because there's no vasculature. And in our body, it's normally within a couple of hundred microns of a blood vessel. Everything is. Weirdly, cartilage isn't. But even with cartilage, when you engineer it, this is actually a cross-section of tissue-engineered cartilage. So it takes about, say, 4 or 5 weeks to grow. And this is the extracellular matrix, the sort of stuff the cell produces, which is actually a cartilage. You get this big hole in the middle. And the question was, could we make an engineered protein, a supercharged myoglobin protein, that could then work as like an oxygen backpack for those cells, so that when things get bad, they can just borrow that oxygen and everything will be okay. And to cut a long story short, and a huge amount of work by the PhD student, it did work. And so this is just showing here what happens when you do have it, actually going this way. So this is this central zone necrosis where all the cells have died in the center. This is where we've actually made an apo version of myoglobin. We've pulled out the bit that does the chemistry in myoglobin and showed that it doesn't work. And then when we have our system, we get almost complete infill. So we had this artificial membrane binding protein supplying oxygen to these cells over that period of time and really improving the quality of the cartilage that you could do. So that was really the first sojourn into, I guess, into stem cells, and I haven't really left that space. The next thing, I guess, was inspired. This is another strange one. You should always go to talks outside of what you do. So we had a microbiologist that was presenting, and part of the work was on the correlation between bad oral hygiene and heart disease. And some of you would know this, but it's so we have this. If you have bad oral hygiene or lots of bacteria in your mouth, there's a type of bacteria called Strep gordoni, which is normally okay in your mouth. It lives in there. I think it's opportunistic, Daryl. Where are you? It's not commensal. It's opportunistic, right? But if it gets in your bloodstream, it can cause infective endocarditis. And what it does is it actually has these special proteins on the outside of it that enable it to home to damaged heart tissue, and it causes these infections. And so I went, I wonder if we can stick these on stem cells. We can hijack this homing property, because one of the issues with cell therapies, especially post-myocardial infarction after you've had a heart attack, is that when you inject all the cells into someone, they just go straight to the lungs. You can never get them on site. And so I was like, this would be an interesting way to actually get them to actually go where they're supposed to go. And so we quickly built this. Where's Tom? Knocked it out. No, this is extremely difficult protein to build. So it's interesting, and Tom's PhD was all about this. So it has what we call an intrinsically disordered region, but it's what we call a high KD. It doesn't bind things very strongly. It fishes around for its target. When it finds it, then we have this change in the shape, the conformation of the protein. It binds really strongly. And then we fuse this to a supercharged protein. So rather than doing it the way we did it chemically, we did it recombinantly, and that would then embed into the membrane. Okay, so we built this, really hard to build. I'm jumping straight to the chase. It's stuck on the cells really nicely. There's a huge amount of work that goes with this. And we started collaborating with a group in Australia who work on these kinetic models of where cells go when you inject them into murine systems. And this shows really one of the most nervous sort of sets of experiments. I wasn't there for it, but it's injecting 10 million human stem cells into the left ventricle of a mouse to see whether or not this works. And it worked, which was pretty amazing. I remember getting the email from my collaborator in Australia going, thank you for your beautiful protein. It was such a nice email to get. So yeah, it was really inspiring that this sort of technology worked. And then the last, I guess, little story on, on this sort of tech at least with tissue engineering, was this idea of could we sort of hijack the wound healing process a little bit? So when you cut yourself, there's a cascade of biological processes that go on, but you end up essentially clotting, right? And partly how clotting works is we have an enzyme called thrombin. It snips something off another biomolecule, and you get fibrin, which is a hydrogel. And the question was, if we could put artificial membrane-binding thrombin on the outside of stem cells, could we get it to actually grow a hydrogel from the surface of this? So we wouldn't even need a scaffold. We'd have a completely scaffold-free tissue engineering approach. And so this is the sort of concept here, that here's the cells, and here's this artificial membrane-binding thrombin, and then the fibrinogen is there, which is in our blood normally, and then it would just grow that gel. And on the left, I really love this sort of movie, is the cells are basically in purple. This stuff's in purple. The green is the fibrin growing straight from the stem cells. So it was really, really cool piece of work. And we sort of looked at these in more detail with light microscopy, which is amazing these days. And then also looked at compression analysis. So when we do tissue engineering, we try to do the biology well, but you also have to do the sort of engineering well and understand what you've actually made. And so this is sort of interesting. If you have these systems with stem cells and we're compressing these, so literally squashing these and measuring how stiff they are, you can see the undifferentiated cells, so just normal stem cells, have a stiffness of about 15 kilopascals, and then if you turn them into fat cells, they get about 26, and if you turn them into bone cells, they start to jack up to about 34, 35. So it was really nice to demonstrate this tech could be used. It would still support the stem cell differentiation. And it really we're sort of thinking about active cell-containing wound glues. Okay, I'm gonna have a little drink now. It's been belting along there pretty well. You guys all surviving so far? Good. Cheers. Right. So bioprinting. Where do we start? It was Hagen. He was one of the first people I was sort of doing this with. So there's some really early work on this idea that you could 3D print with stem cells. And so I got very interested in that because it combined a lot of things that I loved. It combined material science, hydrogels, stem cell biology, all these things, engineering mechanics, the lot. And so I wish George Banting was here tonight because he was really supportive, actually, at the time of helping me set up a center. And we have a number of projects that are ongoing on using bioprinting, and I'll explain a little bit in a second. We have some sort of cartilage bone engineering. We have some work with GSK where we actually 3D print stem cells onto human teeth to try to sort of recapitulate that sort of dentine bone interface. I'm going to talk in some detail about this colorectal cancer spheroids because I think this is a really important area. Some work with aerospace engineering where we look at natural fiber composites and start building those in with Fabrizio Scarpa, who's somewhere in here. Hi, Fabrizio. And most recently, actually, we're really starting to move into this idea of engineered living materials and bacterial microreactors, which I'm very excited about. But this is the evolution from 2014 to sort of now. So back in 2014, any PhD student who joined the group who was working on this, it was flat packed, here's your printer, right, which is just a plastic printer. Now you need to turn that into something that can print stem cells. And so everyone had their own designs and everyone would build these. And it was, to be honest, it was incredible training for a PhD student. And then I convinced George to give me some money, going, look, this is important, and we need to be able to teach other people to do this, not just people in my group, but to really expand this out as a capacity, because it's a very powerful technique. And then we built the sort of bioprinting center in Bristol, I guess, 3 or 4 years ago. My group was also fairly happy, I think, about getting commercial systems as opposed to these. And so some very basic chemistry for how the sort of first ink, or there's lots of variations of this now. We have 2 polymers in there. We have chlorinic F127, which is an industrial polymer. and we have a sodium alginate, which is like a seaweed polymer. The thing with the bioink and the idea of bioprinting is that, basically you have a needle here, and inside that you have cells and you have the bioink, okay? So you're not just printing a scaffold and then putting cells on. You have to create a special type of ink that supports the cells, keeps them alive, and you have to print with both of them at once. Okay, so, that's sort of a challenge. And so we came up with a system which had F127, so it has to start off as a liquid and become a solid, obviously. So this one has a sol gel transition that's based on temperature. And this one you cross-link with calcium. And the idea was you would print it at room temperature with the cells onto a 37-degree bed, then it becomes a solid. Then we give it a bath of calcium chloride, and then actually all this came out, and then you end up with your structures. And what was interesting was that we ended up with these microporous materials, which was really nice because you want to get as many nutrients through these gels as possible. I would like to say we planned this, but it really wasn't like that. And this was some of the really early work where we're really demonstrating that structural fidelity, on how big a structure you could print, how thin you could go. And then I guess what we were doing, which a lot of people weren't doing at the time, well, not too often, was then doing full tissue engineering and cartilage or bone engineering on the structure. So we were printing. A lot of people were printing. It was such a new technique that you could print something, look at it for 2 weeks, and then publish it. It was so new. And so we did a lot of work of really pushing these through these tissue engineering protocols that we knew. And I do like this figure because this is histology where we're looking at different types of VCM. And there's a reason why it's so blocky is because every single block is a slice that's been carefully reconstructed and probably took hundreds of hours by the PhD students who did it. So I'm going to sort of move into the last little sort of section. And, this is, I really like this work, and I think it's very important. And one of the nice things about bioprinters is that, or bioprinting, is that, it's just a robot, really, that dispenses. And robots are really good at doing the same thing over and over again. And so when it comes to biology, one of the big issues we have in biology is that you need to do things over and over again because there's so much intrinsic chaos variation within biological systems that you quite often need to have extremely high, what we call N numbers, to do something. And so we were interested in moving into this area of printing basically baby cancers, what are called cancer spheroids. And part of this is through discussions with a young colorectal cancer surgeon, Adam Chambers, and also Ann Williams, who's in my school. This is one of the wonderful things about being in a school surrounded by, as I call it, all the ologies, immunology, biology, anyway. So we set up a system to do this. And the idea was that we would be able to take a biopsy from a patient. And it wasn't about discovering new drugs. It was about discovering people that would respond or wouldn't. And one of the issues with chemotherapy is that, or even adjuvant therapies where you have chemo plus radiation and surgery, is that some people, especially the chemo, just simply don't respond. And so all you do is you make their life shittier, and they make them sicker. So even knowing that, we can't even do that now. And the idea was like, could we get to a point where we can now start to actually make a good decision on what sort of therapy someone could get? And to do that, we need to work with very, very small amounts of cells. There's lots of ways of making spheroids, but by printing them from individual cells and having them grow into spheroids became very important. And so the idea was we would have a cell sample, gel prep, we'd print it, measure it. This is the part of the hard bit, because we were using high content imaging, huge amounts of data, and be able to pull out this information of what's happening to these things. And then automate the entire process. And a very talented PhD student who was co-supervised by Hagen, actually, who came in from engineering and had to learn how to do cell biology, basically, and luckily was very good at doing that. So this shows you some of the structures that you get from these printed systems. And there's lots of sort of attributes that you're sort of going for. And it's this idea that, spheroids, a spheroid's much more similar to a real cancer than a monolayer of cancer cells, right? This is the whole point. That if you just have cancer cells in a dish and you put the drug on them, you'll get some information, but quite often it doesn't recapitulate what the real biological system is. So you want to be able to access something more sophisticated. You can go to animal models, but sometimes animal models are not appropriate for the type of things that you're trying to target. Plus, you'd like to reduce the amount of animals that you're using if you can. And so we look at these in detail in terms of, what's the extracellular matrix produced by these cancer spheroids. We look at hypoxia, again, similar to what I was talking about before. A lot of tumors are quite hypoxic inside of them, and it's part of why a lot of the therapies don't always work very well. And so we ended up with these really beautiful structures, and they worked really well. This is sort of the software that we developed in-house. to really find. Imagine you're imaging this plate, and there's literally hundreds of spheroids in each well, all in different planes in Z. Software has to pull them all out, put them in the same plane, then find out where their boundaries are, then image them, then work out how big they are, then work out how much their size is changing. And that's what the software does. And so we ended up with these dose response curves of 2D versus 3D, and it's not a surprise that they're different. What was, this is a whole lot of different types of colorectal cancer cell lines with 2 different types of common chemotherapy drugs. But we could see there's a big difference with 2 and 3D. But what was really interesting was that the response to the different drugs varied a lot between the cancer cell lines and between 2D and 3D. And this really related to, the molecules themselves. Like if you have a small molecule and it has to go inside a cell to kill it, that's fine. If the molecule is different, it might be a little bit different. But if you have that molecule that has to go all the way inside of a spheroid to kill something, it can be very different. So, so this is a really, really, I think, important piece of work. Okay, so we're nearly there. As Winston Churchill said, now this is not the end. It's not even the beginning of the end. It is perhaps the end of the beginning. But actually, it's nearly at the end. So I'm now going to change over to the second talk, which is very short. And something you should never, ever do is take a risk and see, the wheels are coming off. Here we go. I think I just opened the same one again. Let's try that again. Right. So I haven't mentioned CytoSeq yet, and I think, I guess it's partly a journey to translation. So Vlad was talking about how you change and what you learn and what you do. Now, I've shamelessly stolen these slides, which are really new from CytoSeq and a former PhD student. And I can honestly say that the environment in Bristol in terms of setting up and spinning out a company is phenomenal. And I think it's probably one of the best places, if not the best in the UK right now to be working in as we talk about deep tech. So I spun CytoSeq out at the end of 2017, really on a very modest sort of investment. We had a VC on board for a very small amount, and I didn't want too much money because I really didn't have a clue what I was doing. And we actually started off right immediately working on maybe cardiac cell therapy, so we straight away moved into oncology and cell therapies for oncology. And basically, a lot of you probably have heard of CAR T cell therapy, which is super exciting. It's sort of the first ever living drug, right? And so what's done is that you basically take blood from someone, you purify out their T cells, you can genetically modify them to recognize the cancer cell that you're targeting. You activate those, expand those, you give them a treatment of chemo before, and then you reinfuse those and they go in and they kill the cancer, which is just phenomenal when you think about it. I mean, it's this next level of, I think, of technology and medicine. The issue is that it only works for hematological tumors. It doesn't work for solid tumors. And solid tumors are responsible for about 85% of the deaths by cancer. So this is a real issue. And it's an interesting challenge as a physical scientist, because you have physical barriers to getting the cells into that solid tumor. You've got this environment which is not amenable to T cell response, immune cell life. There's active immunosuppressive factors in there. And so CytoSeq's whole vision is to basically augment these cells to try to overcome those solid tumor problems. And I think the way we do this is really, again, building off this work, which is the last 10 years of work in my lab, to build these designer molecules. And in CytoSeq, we do it really well now. And we build basically specialized anchor domain, and on the outside we have this functional domain. And these, obviously I can't talk about them. My CEO's around here somewhere, and she'll have the knife out if I say too much. But we're getting some very, very exciting results. This is some of the early work just showing it on the outside of T cells. But things like T cell expansion is hugely important. We can see that from our technology. T cell activation is super important. And this is actually showing tumor killing now. So this is looking at when we modify these immune cells with our technology, they kill cancer cells much, much better. So it's very exciting. So this is the end of the talk. And rather than run through the huge list of people I want to thank, obviously I want to thank all of you for coming tonight and putting up with me. And those who've traveled in particular, it's been great. I thought I'd just pull out a collage of people that I'd like to thank. There's one coming up with you, Hagen, I think that I like. Tavs, obviously my mum and my sister in that photo. Joe Harrison couldn't be here. Duncan McGillivray. I'm not going to run through all the names. But yeah, thank you very much, and looking for a beer. Pete, obviously. All right. Cheers, guys.
Thank you very much, Adam. I think your second set of slides are a lot better than your first set of slides.
I know.
And I think you nicked one of Valeska's diagrams in there, by the way. It was very similar.
Yeah, we published it twice as well. I probably just want to thank, there's a lot of group meeting photos in here because ultimately, it was the PhD students and the postdocs that really did all the work for the most of my career. And I think that's the same, any professor, it's always the people that are in the lab that are slogging it out that are the ones that really make the difference. So thanks to the group, and thanks for coming tonight. I do really appreciate it. I know it's hard to believe sometimes.